Welcome to part 3 of the video podcast series here at Ontario High School of acid-base fundamentals. We're going to talk about pH and pOH, uh, and in the context of strong acids and bases. The next part will have to do with how to find them with weak acids and bases, but for right now, just with strong acids and bases. So stay tuned. Essentially, pH is a measure of the acidity or basicity of an aqueous solution. And basicity, it's a hard word to even say, basicity is also referred to as the alkalinity of a solution. So those of you with swimming pools at home or a relative with a swimming pool, or if you work at a pool, you know that it's real important to measure the pH of the water, and then you add certain things to the water in order to adjust the pH. So if the pH is less than 7, it's considered acidic. If it's greater than 7, it's considered alkaline or basic. Your body has a pH of about 7.40. So we try to adjust things that have to do with the body to a pH close to that so that what we expose ourselves to is not irritating to us, at least in terms of pool water, shampoo, things like that. So these are some helpful equations if you'll write these down, and as we go through this you'll see that pH is equal to the negative log of the H plus or H3O plus concentrations. pOH is equal to the negative log of the hydroxide ion concentration. Kw, or the ion product of water, is equal to 1 times 10 to the negative 14th, and the ion product is equal to the concentrations of the hydronium ion H3O plus times the concentration of the OH minus. Now you can substitute H plus for H3O plus. They're used interchangeably in chemistry, but that ion product, or Kw, is equal to 1 times 10 to the negative 14th. So the bottom two equations bear a close look. An easy way to concentrate the H plus concentration if you have the pH is just to take 10 to the negative pH. To find the hydroxide ion concentration, easy way to find it if you know the pOH is to just take 10 to the negative pOH to find that. One of the keys here, and this equation isn't listed, but it would be good if you write it down, just as the concentration of H plus times the concentration of OH minus is equal to 1 times 10 to the negative 14th, the pH plus the pOH is equal to 14. And that relationship will be very helpful to you. pH plus pOH equals 14. When we want to find the pH or pOH for a strong acid or base, it's really pretty simple, because we understand that strong acids and strong bases ionize 100% in aqueous solution. So, for instance, if we look at a 0.1 mole per liter solution of HCl, when it ionizes, you'll get 0.1 mole per liter of H plus, or we could say H3O plus there, and 0.1 mole per liter of Cl minus. When we have 0.1 mole per liter of sodium hydroxide in water, we'll get 0.1 mole per liter of sodium ion and 0.1 mole per liter of hydroxide ion. It's no mystery as to what the concentrations of each of the ions are, and that's what is going to be the key to determining the pH or the pOH. When we look at a polyprotic acid, in this case a diprotic acid H2SO4, one of the things that we've talked about before is that sulfuric acid, H2SO4, only ionizes the first hydrogen 100%. So if we have 0.1 mole per liter of H2SO4, we'll get 0.1 mole per liter of H plus, or again, you can substitute H3O plus if you wish, and 0.1 mole per liter of HSO4 minus. Now, the HSO4 minus will ionize a very small amount of hydrogen, and we'll talk about that when we get into weak acids and bases. The amount that it ionizes is so small in comparison to what the first hydrogen being ionized is, that we pretty much ignore it when we come to finding the pH of an H2SO4 solution. Now, for calcium hydroxide, which has two hydroxides per calcium hydroxide formula unit, In this case, if we have 0.1 mole per liter of calcium hydroxide, we'll get 0.1 mole per liter of calcium ion, but we're going to get 0.2 moles per liter of the hydroxide ion. The subscript 2 would be multiplied by that concentration to get the concentration of the individual ion. So that's very important when you're dealing with strong bases that have more than one hydroxide ion per formula unit. Be sure to multiply the original concentration by the subscript of the hydroxides to get the true value of the hydroxide ion concentration. Well, let's do some calculations. We want to find the pH, the pOH, the concentration of hydrogen ion, and again you can interchange that with hydronium ion, and the concentration of hydroxide ion for the following solutions. So we're going to go with a 0.0025 mole per liter HCl solution, a 0.0025 mole per liter sodium hydroxide solution, a 0.00150 mole per liter sulfuric acid solution, and a 0.00150 mole per liter calcium hydroxide solution. My recommendation is that you pause the podcast, write these down, and try the calculations on your own and see how you do. If you're totally lost, go ahead and resume the podcast and watch to see what I do with the first two, with the HCl and with the NaOH. Then pause it again and see if you can do the final two on your own. But I wish you well. Use the helpful equations, and I'll see you back here momentarily. Welcome back. Let's take a look at the first solution to the HCl. We have a 0.0025 mole per liter hydrochloric acid solution. We know that this will ionize 100%, so we'll get 0.0025 moles per liter of H plus and 0.0025 moles per liter of Cl minus. Now we want to calculate the pH first, so it's the negative log of the H plus concentration. So the negative log of 0.0025 is equal to 2.60. Now I need to find my pOH, and we talked earlier how pH plus pOH is equal to 14, so our pOH would equal 14 minus the pH, so 14 minus 2.60 gives us a pOH of 11.40. I still need to find the concentration of my hydroxide ion concentration, and to do that I use the ion product of water. 1 times 10 to the negative 14th is equal to the concentration of H plus times the concentration of OH minus. The OH minus then would be equal to 1 times 10 to the negative 14th divided by the H plus concentration. So 1 times 10 to the negative 14th divided by 0.0025 gives us a concentration of hydroxide ion of 4.0 times 10 to the negative 12th moles per liter of hydroxide ion. That seems like a lot to go through. There's a simpler way. So I show you in this next equation, the hydroxide ion concentration is equal to 10 to the negative pOH. So 10 to the negative 11.40 gives us 4 times 10 to the negative 12th moles per liter hydroxide ion. A quick note, if you're wondering about significant figures, when we report a pH or a pOH, the numbers before the decimal point are not considered significant. So if you have two significant figures, you have to show two significant figures after the decimal point in a pH or a pOH. So how'd you do? Here we have sodium hydroxide, 0.0025 moles per liter of sodium hydroxide would give us 0.0025 moles per liter of sodium ion and 0.0025 moles per liter of hydroxide ion. We're going to solve for our pOH rather than our pH first because we know our hydroxide ion concentration. If we know that, finding pOH is real easy. Negative log of 0.0025, which gives us a pOH of 2.60. To find our pH, we take 14 minus the pOH, which gives us a pH of 11.40. And then I show you two ways on the slide of finding the molarity or the concentration of the H plus. The easiest way is the bottom equation. Our H plus is equal to 10 raised to the negative pH, so 10 to the negative 11.40 gives us a hydrogen ion concentration of 4 times 10 to the negative 12th. Here we have our polyprotic acid H2SO4, but it only ionizes the first hydrogen 100%, so that's what we're going to deal with here. So if we have 0.00150 moles per liter of H2SO4, we'll get 0.00150 moles per liter of H plus, and then 0.00150 moles per liter of the hydrogen sulfate ion. Our pH is equal to negative log of the H plus concentration, so the negative log of 0.00150 is 2.824. Notice three significant figures here because of the three significant figures in the molarity of the sulfuric acid. The pOH then is 14 minus the pH, 14 minus 2.824, which gives us a pOH of 11.176. I need to find my hydroxide ion concentration. Again, I show you both ways, but the easiest way is to take 10 to the negative pOH. So 10 to the negative 11.176 gives us a concentration of hydroxide ion of 6.67 times 10 to the negative 12th moles per liter hydroxide ion. Finally, let's look at our calcium hydroxide. Now, when calcium hydroxide ionizes in water, we'll get 1 calcium for every calcium hydroxide formula unit and 2 hydroxide ions for every calcium hydroxide formula unit. So if we have 0.00150 moles per liter calcium hydroxide, we'll get 0.00300 moles per liter of the hydroxide ion. You just take the subscript 2 times the original molarity, and that will give you the molarity of the ion. We find our pOH, the negative log of 0.00300, and it gives us a pOH of 2.523. Now, we've found our hydroxide ion concentration, we found our pOH, we next find our pH. It's just 14 minus the pOH, so 14 minus the 2.523 would give us 11.477. And then we're going to take that 11.477, which is our pH, and we're going to find the H plus concentration by taking 10 to the negative pH value, which is 10 to the negative 11.477. And when we do that, we get a concentration of 3.33 times 10 to the negative 12th moles per liter H plus. So that is how you deal with a strong hydroxide that has more than one hydroxide per formula unit. So how'd you do? Well, we are at the end of part 3 of the acid-base fundamentals video podcast series here at Ontario High School. There are several more to come, so stay with this. I'd like to leave you with a quote from my favorite Greek philosopher, Epictetus. "If you seek truth, you will not seek victory by dishonorable means, and if you find truth, you will become invincible." I wish you well.